Ever wondered why the laws that govern large objects don't seem to apply to the atomic world? Welcome to Investigating the Universe, where we embark on a voyage through the realms of classical and quantum mechanics. Today, we're on a mission to uncover the fundamental disparities between these two fields that define the behavior of our universe across different scales. Classical mechanics, the science of the macrocosm, guides the movements of planets and pendulums. Quantum mechanics, the science of the microcosm, on the other hand, reigns over the bizarre and elusive world of particles. Why are these two realms so vastly different? What makes an electron differ so much from an apple falling from a tree? These are the questions we'll be exploring in our journey today. So buckle up as we dive into the fascinating world of physics to uncover these mysteries. Let's get started. Scale is a fundamental differentiator between classical and quantum mechanics. When we talk about scale, we're not just talking about size, we're talking about the realm, the domain, the theater where the action of physics takes place. In the grand theater of the macroscopic world, classical mechanics takes center stage. This is a realm where objects from apples falling from trees to planets orbiting stars abide by laws that allow them to have well-defined positions and velocities. It's a world where Newton's laws of motion reign supreme and everything behaves in predictable and intuitive ways. But if we take a quantum leap into the microscopic realm, things start to get a little strange. Here, in the world of the very small, quantum mechanics comes into play. This is a realm populated by particles like electrons, protons, and photons. Here, particles don't just have well-defined positions or velocities. Instead, they exist in a state of flux, embodying a peculiar concept known as wave-particle duality. In this quantum world, particles can behave like waves, spreading out and existing in multiple places at once. They can also behave like particles, concentrated in one place. It's a strange and counterintuitive world, but it's the world that underlies everything in our universe. So, size does matter when it comes to the laws of physics. From the grandeur of galaxies to the smallest particles, different rules apply. And understanding these rules helps us understand the universe itself. Classical mechanics is all about predictability, while quantum mechanics thrives on uncertainty. This dichotomy can be traced back to the philosophical underpinnings of these two theories. Classical mechanics is deterministic, meaning if we know the initial conditions of a system, such as the position and velocity of an object, we can predict its future behavior with absolute certainty. It's like knowing the precise angle and force with which you strike a billiards ball. You can predict exactly where it will end up. On the other hand, quantum mechanics is probabilistic, introducing an element of randomness into the mix. It's not as if we can't measure things precisely, it's that the universe itself, at its most fundamental level, is a game of chance. It's about possibilities and probabilities. In the quantum world, particles do not have definite positions or velocities until they are measured. Instead, they exist in a haze of possibility, described by what's known as a wave function. This wave function gives us the probability of finding a particle in a particular place at a particular time. So, in the quantum realm, we have to abandon the comfort of determinism and embrace the uncertainty. It's as if the universe is saying, you may know where the billiards ball started and how hard you hit it, but you can't know for sure where it will end up. In the quantum world, uncertainty rules. While classical objects follow clear paths, quantum particles dance to a different tune. Imagine a ballet dancer spinning gracefully on stage. In the classical world, you could predict her trajectory and calculate her future positions. But in the quantum world, things aren't that straightforward. Instead of dancers, we have particles. And these particles don't just spin in one direction. They exist in a cloud of possibilities, described by something called a wave function. This wave function describes the various states a particle can exist in, like a dancer who could be spinning, jumping, or standing still all at once. But here's the catch. This quantum dancer doesn't choose a move until the spotlight of observation shines upon her. Until then, she exists in a superposition of states, a blend of possibilities. It's only when we decide to observe that she chooses her move and the wave function collapses to a single state. This isn't just theoretical musing, it's been experimentally confirmed. For instance, electrons in an atom don't orbit the nucleus like planets around a sun. as we might expect from a classical perspective. Instead, they exist in a cloud of probabilities described by their wave function. This quantum dance is mysterious, challenging our intuitive understanding of the world. But it's also incredibly beautiful, revealing a universe that is far more complex and fascinating than we could have ever imagined. It's a quantum dance of possibilities until observation steps in. The Heisenberg uncertainty principle is a cornerstone of quantum mechanics. This principle, named after Werner Heisenberg, a German physicist, is a fundamental theory that asserts an inherent fuzziness in nature. It declares that it is fundamentally impossible to know both the exact position and exact momentum of a particle simultaneously. Imagine trying to observe an electron with a microscope. The more you focus on the electron's position, the less you can know about its momentum, and vice versa. This isn't due to any technological limitation, but rather an intrinsic characteristic of quantum particles. This uncertainty isn't a reflection of our ignorance, but rather a fundamental aspect of the universe on the quantum scale. The principle asserts that a particle doesn't have a definite position and momentum until we measure it. Prior to measurement, these properties exist in a state of superposition, with a range of possible values. The Heisenberg uncertainty principle is a radical departure from classical mechanics, where the position and momentum of objects, like a thrown ball or an orbiting planet, can be calculated with precision. This quantum principle has profound implications, reshaping our understanding of reality at its most basic level. In the quantum realm, the more precisely one property is known, the less precisely the other can be known. This is the heart of quantum mechanics, a realm where uncertainty rules and our classical intuition takes a back seat. Superposition and measurement are key to understanding quantum mechanics. Picture a quantum particle in a state of superposition. This means that the particle isn't in one state or another, but rather, it exists in multiple states simultaneously. It's as if our particle is in many places at once, each with its own probability. This concept is a core tenet of quantum mechanics, and it's one of the many ways this field departs from classical physics. Now let's add the act of measurement into this mix. In the classical world, we think of measurement as a passive act. We observe, we measure, and the system remains undisturbed. But in the quantum world, things aren't that straightforward. Here, measurement plays an active role. When we measure a quantum system, we force it out of superposition. The particle collapses into one state and all other possibilities vanish. This is known as wave function collapse. Interestingly, we can't predict which state the particle will collapse into. We can only determine the probabilities of the possible outcomes. This randomness is another fundamental departure from classical mechanics, where outcomes can be precisely predicted given initial conditions. There's also an intriguing phenomenon called quantum entanglement. If two particles are entangled, measuring one directly influences the state of the other, no matter the distance between them. This spooky action at a distance, as Einstein once called it, challenges our conventional understanding of space and time. So you see, quantum measurement is far from passive. It's a dynamic process that directly influences the system. It's as if the very act of looking changes what we see. This peculiar nature of quantum measurement has profound implications, not just for physics but for our understanding of reality itself. Measurement in the quantum world is far from a passive act. One of the most mind-boggling concepts in quantum mechanics is wave-particle duality. This is where the quantum world takes a fascinating twist, defying our classical understanding and intuition. Let's unravel this enigma. In the macroscopic realm of classical physics, we're accustomed to seeing objects as either particles, like billiard balls bouncing off one another, or as waves, like ripples spreading across a pond. But the quantum realm doesn't play by these rules. Quantum entities, like electrons, photons, or even atoms, refuse to be pigeonholed into just one category. Instead, they exhibit the characteristics of both particles and waves. Yes, you heard it right. They can behave as discrete point-like particles and also as spread-out undulating waves. This is the essence of wave-particle duality. When we shoot electrons towards a wall with two slits, we'd expect them, as particles, to pass through one slit or the other, creating two distinct spots on a screen behind. But that's not what happens. Instead, we observe an interference pattern. a series of light and dark fringes, akin to what we'd see if waves were passing through the slits. This suggests that each electron, as a wave, passes through both slits simultaneously and interferes with itself. But here's the catch. If we try to determine which slit the electron goes through, it behaves like a particle again, passing through one slit or the other, and the interference pattern vanishes. It's as if these quantum entities are saying, "You can't pin us down. We'll behave as particles when you're watching, and as waves when you're not." This wave-particle duality is a cornerstone of quantum mechanics, and it's a stark departure from our classical intuition. It challenges our understanding of reality, pushing us to reconsider what we think we know about the universe. Quantum entities defy classical categorization, behaving as both particles and waves. Our journey through classical and quantum mechanics reveals a universe of complexity and wonder. We've traversed the macroscopic realm where classical mechanics rules, with its predictable, well-defined objects. Then we've dived into the microscopic world of quantum mechanics, with its inherent uncertainty and the fascinating concept of wave-particle duality. In the realm of the quantum, particles exist in a spectral dance of potential states guided by wave functions. The Heisenberg uncertainty principle reminds us of the impossibility of simultaneously knowing a particle's exact position and momentum. And let's not forget the intriguing concept of superposition, with particles existing in multiple states until measured, a process that actively influences the system. Our exploration of these two contrasting realms underscores the richness and complexity of our universe. From the deterministic dance of everyday objects to the probabilistic ballet of quantum particles, each realm has its own rules and wonders. Remember, the universe always has more mysteries to unravel. Until next time, keep questioning, keep exploring,